So welcome to our presentation. Today we're going to talk about ChatGPT and large language models. Before we do that, let's introduce ourselves. So this image is generated by AI, by the way, with a prompt. So I'm Pantelis. I have graduated from the mathematics department here at University of Crete. I have a master's degree in data science. I enjoy working with data-driven technologies, and I'm interested in machine learning, data science, natural language processing, and data engineering.
Right. Hello from me also. I'm Dimitris. I'm also a data scientist and a mathematician. My focus areas are distributed computing, databases, cloud, and ML, and I'm a huge fan of big data and AI.
So our presentation is split in two parts. The first part is an introduction to large language models. So we will have an introduction about some concept about what artificial intelligence is. We will talk about neural networks, transformers, these huge models that have appeared recently, and we can train models like GPT and ChatGPT with them. So let's see what artificial intelligence is and what are its subsets. Artificial intelligence is any machine that seems to be able to act in a way similar to humans and make decisions. Machine learning is a subset of artificial intelligence and refers to models that can learn from complex data without being explicitly programmed. Deep learning is a subset of machine learning, and it refers to big algorithms, big networks that are inspired by the way our neurons in our brain work. Today we will talk about NLP tasks, natural language processing tasks. In simple words, NLP processes human language for computers. It can convert text into structured data for making further analysis. It can understand, interpret, and even generate text. Some of its applications are chatbots, translation, sentiment analysis, for example, amongst others. It combines linguistics and machine learning. And it can enable automated text-based tasks like question answering systems, like making some resume of a text. But who is more responsible, more good at explaining what a natural language processing system is than a natural language processing model? So the previous slide was actually generated by NLP. I gave it a prompt, and it was actually to be able to generate a very precise and in a good way explain what natural language processing is. So I'm sure you have already tested it, but we can all see how powerful these models are. And now let's talk about the fundamentals behind natural language processing. So let's talk about neural networks. Neural networks are inspired by the structure of the brain. They're not a new concept. They were introduced in 1943 in attempts to find mathematical representation of information processing in biological systems. They are actually neurons interconnected to other neurons, creating a network, as you can see in the image at the bottom left. So there are neurons, there are layers that go through the network. They form the base of deep learning. When we have these networks that have a lot of layers, then we have deep neural networks. They can be applied to data like text, images, sound, videos. And the idea is that the input goes through the layers and it produces an output. In order to explain a little bit better how these networks work, I have created some hypothetical research data that compare, depending on the training volume that the person does, the health condition that this person might have. So we have a health condition indicator here, with 0 being that he or she is unhealthy, and 1 being health condition. We can see that for low values of training volume, it is associated with not that good health condition, with moderate training volumes, with good healthy conditions, and with when someone does excessive training, if someone overtrains, this is related with an unhealthy condition. We can see the problem here is that we're going to be able to predict, given a training volume that we have not seen before, we're going to be able to predict what health condition this person might have. So this cannot be done by a line. So if we draw a line to the data, in some cases it might seem okay, but for example here, if the training volume is excessive, we will not make a good prediction. The same holds for this case too. So in order to be able to explain our data a little bit better, we probably want something like this. So we're going to add some curves in our line. Okay, and okay, and now let me explain how this is done in a very simple neural network. In our example, there are just 3 layers: an input layer, just 1 hidden layer in the middle, and 1 output layer. These circles are called nodes, and they are connected to the other nodes with directed arrows called connection. So at first, we have a training volume that we're going to train our model with. This is a value, this is a scalar value. So this will be multiplied by some weights, and these numbers here, denoted by B, are called biases, and this will be added to in the equation. When we go to the hidden layers, there are some activation functions that add this curvature in our model, so they are not linear. And this, what was produced by the weights and the biases, will be inserted inside these functions. And in our case, eventually we will again multiply by the weights and add the base, the bias, and in the output layer, we will have an output for health condition. Initially, the model, the weights and the biases of the model will be randomly initialized. So our prediction will not be that good at first. And now let's see how our model learns. So in this step, we have made a prediction for the specific training volume that we gave the model. We know the actual value that we expect, the actual value for the health condition that we expect, and these are called label data. So if we know what we expect, they're called label data. So we have a prediction. We have our label, so we can compare them. We can use a cost function and compare these 2 values. The whole process is done in order to minimize the cost function by changing the weights and the biases inside the network. So in all of the layers, we will go back and update these biases and these weights. When this procedure happens for a lot of examples, our network learns. So the end goal here is given a value, an input value that it has never seen before. We want our model hopefully to predict something as an output that will have a good accuracy. And now, let's play a little bit with that. Okay. So I'm going to show you here a neural network that has 2 input nodes, 4 nodes in the hidden layer for neurons, and 2 output nodes. In this case, as you can see here, these 2 different classes, different data can be easily separated by a line. We can just fit something like that. So we could use an activation function that is linear. This is an easy problem. It can easily do that. But if we have something more complex, we see here that these are not easily separated with a line. So, okay. So we want something like that to separate them. So as we can see here, if we use a linear function, it struggles a lot. It cannot find a way to separate them. But with a different function, we can see how easily it can do it. Okay. Of course, these models can be very deep. They might have a lot of layers, and they might also have a lot of nodes in this layer. For example, here we have a problem where we're trying to predict, given an image that the network has not seen before, if this image represents a dog or a cat. So this is a trained model. So the image will get inside the network, and it seems that it is able to predict that it is a dog with a good accuracy. And now let's talk a little bit more about large language models. There are deep learning algorithms that are able to perform very well on text-related tasks. But why now? Why are they so, they have increased their popularity now? LLMs have actually been around for more than 20 years. But recently, there were some huge developments in deep learning and AI algorithms. Also, we now have better computational power offered by GPUs. We can also find very large data sets. So now large language models can achieve much better results, and that's why they are now more popular. Some use case examples from large language models is content generation, cooking suggestions. They can be used as coding assistants to make conversations, for language translation, and also customer support. But let's see what was, until not that far ago, the state of the art for this model. Recurrent neural networks were the state of the art until recently for text-related tasks. They're used for data that can be interpreted as sequences of characters. So this might be a time series data, text, for example, sound, this kind of data. Some examples that they might be used is for speech or text processing, music generation, and others. They are able to process data sequentially, so each word at a time. Yeah, they look at the sentence one word at a time. They have a hidden state that acts as the memory inside the network. So in the example here, we ask what time is it? Let's say we want to process that with a recurrent neural network. We can see that in the second step, when we refer to the word time, with a dark blue color, it has some memory of the previous word that is what. And this continues for the next word too. So in each step, it has some memory of what words have appeared until now. But recurrent neural networks have some problems. They actually do not perform really well for large texts. They might forget if they're in a large text what was happening in the beginning if they're at the end. Also, it's a sequential process, so they cannot parallelize well, and as a result, they are slow. And now, let's talk about transformers that seem to have solved these issues that RNNs had. Transformers are a type of neural network that has sequence-to-sequence architecture. That means that they take a sequence as input and they generate a sequence as output. They were first introduced in 2017 with the paper "Attention is All You Need" from researchers at Google and University of Toronto. And this is a very important paper that changed the way NLP is done now. Yeah, they're responsible for significant improvements in the performance of natural language processing tasks. Now transformers can be parallelized. And with them, very large models like GPT-3 can be trained. Some concepts that we see in transformers are positional embeddings. So for each word that the network sees, it has some information about the position of that word. So the network is able to learn the word order from the data. Another concept is attention. As we can tell from the title of the paper, "Attention is All You Need." Attention is very important in these networks. So by seeing a lot of examples, the network learns in which word to attend when it gives its predictions. Attention was not introduced in that paper. It was actually introduced in 2014 in this paper here. And we have an image from this paper that has a translation task from English to French. So let's read it. The agreement on the European Economic Area was signed in August 1992. We can see that when these words are translated to French, the model has learned in which English word it should attend to. So for example, when it says Européen in French, it attends to mostly to European, or économique in economic. And another concept is self-attention, which allows the neural network to understand the word depending on the context around it. So in this sentence, the animal didn't cross the street because it was too tired. When the network sees the word eat, it is able to understand that it refers to the animal. And here is close. Okay. Here is the image of how a transformer network looks. The only thing that I want to point out here is that it consists of two parts: the encoder part here and the decoder part. They are trained on very large amounts of unlabeled data. For example, in Wikipedia. And after that, they can be fine-tuned on our specific task. They have this decoder structure, and a lot of encoder blocks or decoder blocks can be stacked the one on top of each other, as it's shown here from the n times encoder. So they can be stacked a lot of the one on top of each other. We can have architectures where we only have encoder blocks. So just this part here. So if we have just encoder blocks stacked the one on top of each other, we have models like BERT, bidirectional encoder representation of transformer. If we have just decoder blocks stacked on top of each other, we have GPT, generative pre-trained transformer. Now let's talk a little bit more about what GPT is. So the main objective in the pre-training phase of GPT is to predict what word will come next. So let's say we have an example sentence. I went for a walk. Our sentence will start with a token, with a word that indicates the beginning of the sentence that I symbolize here as start. This will go inside the GPT model, and it will create a prediction. It will create a prediction for what is the most probable word to come next. On our case, we know that the word that we expect is I. So we can compare that and update the network. After that, start and I will be used as input for our network. This will go inside and predict what word is most likely to come next after these two tokens, these two words. So it will make a prediction. We know the right word. I went for a walk as we read the text. This will be used as input again. And this procedure repeats, and the model eventually learns to become language aware. So yeah, I went for a walk, and this ends. And now we have a pre-trained model. We have a model that has some context about language. And we can fine-tune that model. What does fine-tuning and transfer learning mean? It means that we can have a general model, like the one I explained before, and we can use our own data in order to solve a specific problem, a specific task that we have. And this has shown to have very good results. Some examples of where this might apply is, for example, document classification, question answering, language translation, and others. And now we're going to talk about ChatGPT. ChatGPT actually takes an input prompt and generates a response. But how was it trained? Here is the training procedure of Here is the training procedure of ChatGPT. It's actually split into 3 steps, and we're going to explain all of them now. So in the first step, there are prompts sampled from a prompt dataset. Then we have a human annotator, a labeler, that goes and writes down what's the desired output for this prompt. This data can be used to GPT 3.5 was actually used for ChatGPT, So this data can be used for fine-tuning the procedure that I explained before. For our model with supervised learning. So by repeating that procedure, we end up with a supervised, fine-tuned model. That's here. So this is the output from the first step. The second step takes a prompt and generates several model outputs. Okay. But you might wonder, how can it generate several model outputs? Depending on the previous words, it generates probabilities for what would be the next word. So our model has a dictionary, and it generates probabilities from that for what would be the next word. Let's say that I ask, for example, what we will have for lunch today. And the answer that is generated is today we will have French. And here we have some probabilities about the next word. It might be fries, it might be bread, it might be toast. So one thing that we could do would be to actually just take the most probable word and just have our sentences made this way. So always select the top probability. But this is not the case for human language. We do not always choose the most optimal word. Human language has a lot of variability. So in order to use that, we can select different sampling methods. So, for example, the top 5 probabilities can be selected and randomly sample one of them. So, in this case, the sentences that will be generated will be more random. So this is how different responses are generated here by our model. And then we have a labeler again that determines a value, a reward, depending on how good he or she thinks their responses are. So in Likert score, so for example, from 1 to 7, how good he or she thinks the response is. Then we can take all of these inputs, so the prompt plus one of the responses, and the scalar values determining the quality of the response, and train our reward model. And this reward model will be the output from the second step. Okay. So we can actually play with different ways of producing the next word at OpenAI Playground. So I have an example here. I asked, how was your day? It was good, thank you. And we can see here, I had a productive day. We can see the probabilities for another word to be generated depending on this context would be. And we can actually play with the way that the words are sampled, make our responses more probabilistic or deterministic as we want. And now we can go to the third step. So we have already a reward model from the second step, a supervised fine-tuned model from the first step. And now we can select new prompts from our dataset. We have a proximal policy optimization model that is initialized from our supervised policy. And then, as we expect, it generates an output, it generates a response. Then the reward model from the second step is used, and for this output, a scalar value is a reward is predicted that tells us how good this response was. And with this, we update our model here, and this procedure, this reinforcement learning procedure actually repeats a lot of times, and as a result, ChatGPT can produce more functional, non-toxic, and more human-like responses. We can see here the evolution of GPT models. So we can see that from 12 decoder blocks, the ones that I told you in the transformer architecture that are stacked the one on top of each other. So from 12 decoder blocks, they have increased a lot. From 117 million parameters, we have reached 1.76 trillion. But where can we find these pre-trained models? We can use the API from OpenAI. Of course, it's paid. And we can find models like GPT-3 or Codex or DALL-E for images. And we just can just insert those few lines of Python code and interact with it. Another very popular and useful library for natural language processing, but not only natural language processing, is Hugging Face. So in Hugging Face, we can find and download pre-trained models, and then use our specific task data, then fine-tune them on our specific task, on the task that we want, and have a model that will probably have achieve very good results in this way. Some of the examples of the tasks that we can find models on Hugging Face are those here. And now we have a question for you. We want to see how ChatGPT has come to our lives. So we can scan this here and in real time vote. I think this will be very interesting. We'll give some time. As we expected, multiple times today wins. So now the first part of the presentation will finish. I don't know if you want to ask questions now or at the end of the whole presentation.